and then we have taken the equilibrium equation about the hinge point. About the hinge point, this is K delta is the stiffness of the control surface, that is, or in other way I will say stiffness of the control actuator, and delta minus delta naught is the restoring force. This delta naught is basically the pilot demand of the control surface, but due to flexibility of the control surface, we have actual deformation is delta. Delta minus delta naught multiplied by K delta, that will be the elastic restoring force by the control surface actuator, and aerodynamic moments acting due to angle of attack and also deflection of the control surface. Then we have taken one assumption here, alpha r equal to 0. Why we have taken alpha r? This is just to get a analytical solution whatever we are deriving. But alpha r equal to non-zero value will give a solution, but we may not be able to get analytical solution. We have to go for numerical solution. That is why we have taken alpha r equal to 0, but that is for our sake of the derivation in the current form. But alpha r non-zero value also will be able to get the solution. Only in that case, then we have to write a computer program to get the values, different means for different value of alpha r we can get the solution. Basically in this we have taken two degrees of freedom. One is the theta, that is flexible angle of attack, and another is the delta, that is flexible deformation of the control surface. These are the two degrees of freedom. Associated to these two degrees of freedom, we have obtained two equilibrium equations. Okay. Then I am coming to the first case. I am saying ideal actuator means actuator is infinitely rigid. So whatever pilot is demanding, the actuator will be deflecting to that delta. So there is no, that's why I am saying for ideal actuator, or in other way rigid control surface, we can say that delta minus delta naught equal to 0. That is what K delta we have taken infinitely large value, delta minus delta naught equal to 0. Then in that case our second equation will vanish. So second equation will not exist. In the ideal case, whatever we have considered, ideal case is first case, and in that respect we have now we are defining that first equilibrium equation, whatever we have obtained here, q infinity E c square Cl alpha, alpha r plus theta plus Cl delta by Cl alpha into delta, Cm delta by E Cl alpha into delta, that is equal to k theta into theta. We are now expressing this equation in terms of non-dimensional parameter. So we have taken it here q infinity E c square Cl alpha, and in this case, as I have discussed earlier, so alpha r equal to 0. So I am taking only theta value here, and we are defining Cm delta by E Cl alpha is nothing but Cm delta bar. So Cm delta bar plus Cl delta bar. Similarly, Cl delta bar we have defined Cl delta by Cl alpha, whole thing multiplied by delta naught, and that is equal to 0. So actually the bracket will be ending here. Q E c square Cl alpha into theta with second bracket theta plus first bracket Cm delta bar plus Cl delta bar multiplied by delta naught, whole thing, the second bracket ends here, that is equal to k theta into theta. And from here, rearranging the equation, we can find out the value of theta. So k theta minus q infinity E c square Cl alpha into theta, that is equal to q infinity E c square Cl alpha Cl delta bar plus Cm delta bar into delta naught. So simplifying this equation, dividing whole equation by q infinity E c square Cl alpha, we are getting first equation defined as k theta by q infinity e c square CL alpha minus 1 into theta. This right hand side is Cm delta bar plus Cl delta bar into delta naught. And here we are defining one parameter that we are calling as the QD. With our linear aeroelasticity analysis, what we got, k theta by E c square CL alpha. I am taking that outside, so that I am defining by QD. So this portion is defined as QD. So QD by Q infinity minus 1 into theta. Right hand side is Cm delta bar plus Cl delta bar into delta naught. So solving this, we are getting theta is nothing but Cm delta bar plus Cl delta bar into delta naught. This whole thing divided by QD by Q infinity minus 1. This is the solution of the theta. Now, what we will do, we will next, actually if you look at here, that is what the ideal condition I have defined. So, whatever pilot is demanding the control surface deflection, he is getting that. So, delta and delta naught are same. With respect to that, we have only the equilibrium, the forces whatever is developed, external forces were developed and the internal restoring force is coming into the elastic axis, and then we have using that equilibrium equation we have find out the value of theta. Now, I am coming to the calculation of efficiency. So, in the calculation of efficiency, we are interested to find out the efficiency, the control surface efficiency. That means, we will be calculating aeroelastic lift due to aeroelastic phenomenon, whatever correction is there in the lift force distribution, we are taking that and then dividing by, if there is structure is considered as ideal, no means infinitely rigid, no additional deformation will be there due to the flexibility of the structure, then whatever lift we get, that I am defining as alpha r, rigid rigid L, rigid lift. That is aeroelastic lift is q infinity c into Cl alpha. I am multiplying by theta plus Cl delta by Cl alpha into delta. That is from our lift equation, whatever we have taken. And then we have substituted here the value of lift, value of theta to find out the aeroelastic lift. And the rigid lift is q infinity into c into 1 Cl alpha multiplied by this we have defined as Cl delta bar into delta naught. So, to find out the efficiency, this we call as the control surface efficiency. Basically, efficiency of the control surface, that is what eta delta. Eta is the usually the symbol used in the in our aerospace applications or mathematics. We use eta into eta delta is equal to LAE by LR. Then I have just manipulated here to show what is the value of eta delta, that is the lift efficiency, and when this lift efficiency becomes 0, that I am calling as the control reversal. That is the condition of control reversal, that whatever I have shown it here, if when eta delta is equal to 0, the condition is defined as reversal. That means whatever numerator part of this equation we are getting, we will be equating that numerator part equal to 0. In the earlier case, divergence case, what we got the idea that when theta is infinitely large due to flexibility of the structure, the deformation of the deformation due to flexibility of the wing goes to infinite. In other way, a very high value of angle of attack. Obviously, when it has gone to some high value of angle of attack, the linear theory no longer valid. So, there whatever we have equated, basically the denominator part equal to 0, that gives the divergence condition. Here the efficiency, when efficiency becomes 0, that is basically numerator part of the this efficiency equation becomes 0, that we are calling as the control reversal. Is it clear now?
Yes, sir.
Okay. Then I am just coming to the next part. I am saying that when control reversal equal to 0, I have just taken it from this equation. If you look at here, I have taken the numerator part q infinity qd by q infinity minus 1 then plus Cm delta bar by Cl delta bar plus 1 equal to 0. That is what I have taken it here. See, if you look at Qd by Q infinity minus 1 plus 1 plus Cm delta bar by Cl delta bar is equal to 0. That is basically the numerator part of this equation. What we have considered here, the efficiency, that is I am equating it to 0. And then from here I am getting a condition, means this will in that case after simplification this will be cancelled. So it will become we will get the information about this qd by q reversal is q infinity qd by q infinity. This is the free stream dynamic pressure. Free stream dynamic pressure is equal to minus Cm delta bar by Cl delta bar. If you look at okay, let it be in this form. So this condition basically signifies the control reversal speed. So this q infinity will define that as a q reversal, q infinity reversal, q infinity reversal. So finally we can write as qd minus qd Cl delta bar by Cm delta bar. If you look at here, whatever equation we are getting here, that is what I have discussed earlier day also, we are getting with the negative sign. That means if we take Cl delta bar, Cm delta bar, then it is going to negative direction, means negative direction of the forward speed. Actually, that is not the case. If we look at the means dimensions, we will find that the Cm delta actually will be coming as a negative value. That is what I have discussed here also. The Cm delta bar usually is the negative, less than 0. That is where basically it will be finally coming to Cl delta bar will be positive, Cm delta bar will be negative. With the negative sign, it will become positive. So it will be q infinity reversal is equal to minus q d Cl alpha bar Cl delta bar by Cm delta bar. This is the final divergence reversal dynamic pressure, but depending on the sign of this Cl delta bar, Cm delta bar, it will be finally coming as a positive value of forward speed. Is it okay? Uh, Today actually I have uploaded the PDF file in the dialog box. You can whoever wants to check through that, go through the PDF file, he can download and go through it. If you have anywhere any doubt, you can ask me while discussing this thing. So here, so finally I am rewriting that equation, whatever we have got the efficiency equation. This efficiency equation I am rewriting in the next one. Here Cm delta bar by Cl delta bar, what we got, minus Qd divided by Qr reverse Q infinity reversal R. So if I substitute in this equation, efficiency equation, if you look at here, so I am just substituting in this plus Cm delta bar by Cl delta bar, I am substituting the value minus Qd by Q infinity reversal plus 1, and this equation after simplification we are getting final expression as 1 minus Q infinity by Q infinity reversal divided by 1 minus Q infinity divergence. Now we can have two different conditions to so finally I have shown it here. Q reversal can be calculated as Q minus Qd Cl delta bar by Cm delta bar, and substituting here, if you look at Cl delta bar, we have given as Cl delta by Cl alpha, and Cm delta bar we have defined as Cm delta by ECl alpha, ECl alpha. So, these two I have substituted here. So, E will be cancelled from this equation, where QD we know QD is K theta divided by E C square Cl alpha. So, E C square E will be cancelled from coming from this equation. This E will be cancelled. So, finally, Q reversal speed I can get, that will be equal to minus K theta by Cl alpha into C square and Cl delta by Cm delta. That is the reversal speed. Means you need to get the aerodynamic coefficients, these two coefficients, Cl delta and Cm delta, K theta already known to us, and Cl alpha C square. This is another lift coefficient we need, and the chord length. See, if you look at here, interestingly, the Q reversal speed is, in the first case, is not dependent on the stiffness of the control surface. See, we have taken control surface deflection as K delta, but if you look at here, in the reversal speed, K delta is not coming into picture. Is it clear what I am saying? See, reversal dynamic pressure, as we understand from the previous case, that is the divergence speed is dependent on the K theta, but Q reversal is not dependent on the K delta. It is independent of K delta. It is depending on the overall torsional stiffness of the wing and also aerodynamic derivatives. Is it okay?
Yes, sir.
Okay. See, here you may think that we have considered that the control surface stiffness is infinitely large, that is why it is not coming. But I will take the next condition and show you that Q reversal is actually independent of control surface stiffness. So, here I am just plotting this control reversal means control efficiency with respect to forward speed. So, if first condition we can take when QR is less than QD, QR is less than QD, then we can get one type of equation. Let me just okay, the behavior of the efficiency curve will be getting at Q reversal. If Q reversal is less than QD, at Q reversal it will be 0, and then it will go to infinitely large value of efficiency, negative efficiency, when it approaches to QD, divergence speed of the wing. And this is the reversal speed. What we have taken, reversal speed is less than QD, divergence speed. Next, I am taking when QR, the Q reversal speed is greater than QD, then what will happen? The efficiency will be going this way. Efficiency will be from 1. If you look at here, at Q infinity is 0, this Q is 0, then we will be getting 1. So, that is why the curve is started from 1. So, when QR greater than QD, we will be getting a curve, means with the increased value of forward speed, that efficiency, delta efficiency will increase, and at QD that is the singularity point. So, it will have infinitely large, and then moment we go beyond the QD, so it will be starting from negative value, again it will come to 0 at the reversal speed. This is the efficiency value, and then again it will be increasing. So, this is the nature of the curve whatever we are getting in this expression, what we have finally obtained from this eta delta eta L delta is equal to 1 minus q by q reversal divided by 1 minus q by q divergence, and depending on the value of divergence speed and reversal speed, we are getting two different nature of the efficiency curve. When L alpha are less than sorry QR less than QD, then we are getting this type of curve. When QR is greater than QD, then we are getting this type of curve. At QD there will be a singularity, at QR the efficiency will become 0. Is it clear why we are getting the curve in this nature? Because depending on the design, we may have control surface reversal dynamic pressure will be less than QD or QR greater than QD also. Both the conditions are possible. Means it is up to the designer how they will take the decision, or how the other from other groups the demand is coming. Means basically it will be coming from the control group, whether we need QR greater than QD or QR less than QD, and based on that structural designer has to design the aircraft wing such that the Q reversal will be greater than QD or less than QD. See, these whatever analysis doing, basically our objective is that we want to design an aircraft which will be satisfying our requirement. The requirement is can have infinite values type of requirements. So, depending on what purpose we are using the aircraft, we can have the requirement different, and based on the requirement we have to make our design appropriately, so that it satisfies our requirement. Is it clear? So, now I am coming to again this one. Let us show you this information that when with a line diagram I am showing, this is the wing portion, this is the control surface, and control surface deflection is delta, and the eccentricity between aerodynamic center and elastic axis E into C. So, and the angle of attack infinity is alpha, and the forward velocity is u infinity, and this is the two dimensional aerofoil with control surface. And if we look at the aerodynamic coefficients, Lipps coefficient and coefficient of the moment about the aerodynamic center, we will be getting a equation like this: CL equal to CL alpha into alpha, and CL delta L CL del CL by del delta into delta, and CM will be getting CM alpha into alpha plus del Cm by del delta into delta plus Cm naught, where Cl alpha and Cm naught are respectively the lift curve slope and the coefficient of moment about the aerodynamic center of the aerofoil with undeflected aileron. This is with undeflected aileron. According to the GLUAT, the coefficient of CL alpha, CL del CL and del delta, and del Cm by del delta for a two-dimensional airfoil in an incompressible fluid we can get this relation 1 by A del CL by del delta is equal to 1 by pi arc means cos inverse into 1 minus 2 IC plus 2 into square root E into 1 minus E. Here E is the whatever we have defined, E into C is the control surface control surface chord length. Whatever I have, if I go back, whatever I have taken it here, E into C, this is the chord length of the control surface. The same thing I have used means as per the Gluart, the coefficient will be in this form. Similarly, del Cm by del delta will have minus A by pi into 1 minus E square root E into 1 minus E, where delta is considered in a radian. Obviously, angle will be non-dimensional form, it will be in radian. A is basically CL alpha, that is del CL by del alpha. This is the equation. Then if we look at the reversal speed, whatever we have obtained, the Q reversal is basically K theta E CL alpha into C square CL delta by CM delta. I am just substituting in that expression the value of Q reversal by Q reversal by QD, sorry, Q reversal by QD, whatever we have obtained here, this equation. Basically, in this equation, either this equation or here we have taken, okay, in this equation. So, if you look at that expression minus CL delta bar by CM delta bar, so it will be equal to minus E CL delta by CM delta. So, after substituting the equation, these two equations, if here what we are getting as Cm del Cm by del delta is with the negative sign minus A by pi. So, this same thing we are taking it here. So, it will be cancelled, it will be finally Q divergence, Q reversal by Q divergence will be equal to E multiplied by cos inverse 1 minus 2 IC plus 2 into square root E into 1 minus E, this divided by whole thing divided by 1 minus E into square root E multiplied by 1 minus E. This is considering the two-dimensional aerofoil in an incompressible fluid. This is the condition. What we have considered here, two-dimensional aerofoil, that means the straight angular wing, infinitely large wing for that condition, and the flow is considered as incompressible subsonic flow. Obviously, incompressible subsonic flow. Incompressible, usually the incompressibility experienced in the subsonic flow. That's why we are I am just clarifying that incompressible, but it will be in the subsonic flow. So finally, this Q reversal and Q divergence will get the ratio which will be depending on the value of E, eccentricity between control surface and the aerodynamic elastic axis and the aerodynamic center, and then capital E, the control surface percentage of the control surface with respect to the total chord length. These are the basically parameter. If you look at from here, depending on the requirement, if R is equal to 1, then we will get a curve like this, R equal to 1.05, R equal to 3, like that. We have the relation, means whatever relation we got, if we plot it, we will be getting this type of aileron efficiency plot with respect to the parameter whatever we have considered. So, now from the above curves, it is clear that in order to maintain good aileron efficiency, it is desirable to have Q reversal and Q divergence as close to each other as possible. Both Q divergence, Q reversal are proportional to the wing rigidity and can be raised by increasing rigidity, but Q divergence is proportional to 1 by E, whereas Q reversal is proportional to del CL by del delta divided by del Cm by del delta. Hence, the requirement means we can get ideal condition or optimum condition when Q reversal is equal to Q divergence between the aileron dimensions and the and wing aerodynamic center to elastic axis, the eccentricity we can, and the so finally this we can take a decision that let us say that Q divergence and Q reversal is equal, and at that condition we are interested to find out the control surface length or percentage of control surface length. So, in other way, the two dimensional compressible case, one can get the optimum value Q reversal Q divided by Q divergence is equal to 1. So, finally, we are getting E in terms of the capital E. Usually, we know the elastic axis is located 40% chord behind the leading edge, and the location of aerodynamic center usually for subsonic flow it is quarter chord. So, based on that we can calculate the finally the optimum control surface length is 31%. Just substituting the value relation between these two. For example, if the elastic axis is located at 40% chord behind the leading edge, that means E will be coming as point, in this case 0.15, because location of the aerodynamic center is 25% quarter chord point, and whatever we are taking aerodynamic this elastic axis is at 45%. So, with that combination we will be getting the control surface length is 31%. Is it clear what I am saying?
Yes, sir.
Just I have given a means this is see what we are getting a idea about the control surface length. Suppose we are able to locate a aerodynamic elastic axis as 40% of chord length from the leading edge. Similarly, for subsonic aerofoil, subsonic aerodynamics, we will have the location of aerodynamic center at 25% chord length, that is quarter chord, and substituting this information we can get capital E value. E is coming as 0.31. So, this is the ideal condition if we can maintain the control surface length of 0.31% of the chord length for a aerofoil, where basically if we look at, so we will have a control surface like this. So, this portion is 31% and this portion will have 69%. So, out of total length 69% will be used for the main wing and 31% will be used for the control surface. Now, I am coming to the next condition, case 2, when we have taken K delta is finite. Okay. And obviously, to get the analytical solution, I am just taking alpha equal to 0. With alpha equal to 0, what we got our first equation, is q e c square Cl alpha into theta Cl delta into delta then plus q c square Cm delta into delta minus k theta into theta equal to 0, and then from the second equation, that is q capital E c square multiplied by C mh alpha into theta plus C mh delta into delta minus k delta into delta minus delta not equal to 0. This is the two equations. We can solve directly, or we can approach. I have shown it here from the second equation. First I am calculating the value of delta, because first equation we have this delta is delta is delta can be solved without any trouble, or from the first equation also we can calculate. So from the second equation we have calculated delta, and then this delta we have substituted in the first equation in place of delta, and then finally after simplification we can get the value of theta first, and after getting theta we will be able to calculate the delta value. But that is with the dimensional equation. I am just taking at the alternative form, that is expressing both the equations in a non-dimensional form. So I am taking it here q e c square Cl alpha, then I am defining theta plus Cl delta bar into delta q e c square Cl alpha Cm delta bar into delta minus k theta into theta equal to 0, where I am defining certain parameters like qd wing that we have already obtained. So that is qd wing is k theta by E c square Cl alpha. This is the divergence speed of the wing. Then I am taking another parameter that is q by q divergence. This is q by q divergence. I am taking as a q1 bar. Q1 bar non-dimensional forward speed or forward dynamic pressure. So after simplifying this equation, I am getting it that q into multiplied by theta plus del Cl delta Cl delta bar into delta plus q into Cm delta bar into delta minus q d wing into theta equal to 0, and this equation again I am substituting with the non-dimensional term q1 bar. So it is multiplied by q1 bar into theta plus Cl delta bar into delta Cm delta bar into delta. That is the that I am defining this part, taking this as common, defining that as a B. Cl delta bar plus Cm delta bar is equal to capital B. So first equation will become q1 bar into theta plus b into delta minus 1 equal to minus theta equal to 0. That is the first equation. And from the similarly from the second equation we are defining certain parameter here. I am defining here C, capital C. This is also capital C. CMH alpha divided by CMH delta, that I am defining by C. So if you look at here, first equation will become like this. So it will be Q2 bar. I am defining here Q2 bar is Q by control QD control surface, and here I am taking QD control surface, that is divergence of control surface K delta in the similar form of wing divergence. Here I have taken K delta by E c square CMH delta. If you look at QD wing, we got this way K theta by E c square Cl alpha. I am just equating in a similar form and then dividing means expressing K delta in place of K theta. I have taken K delta. Small e I have taken capital E c square. In place of Cl alpha I have taken CMH delta, because control surface deflection will be inducing the moment coefficient. That's why I have taken it equivalent to that, and then I am defining Q2 bar is Q by QD control surface. So after simplification, we will be getting as Q2 bar multiplied by first bracket multiplied by C into theta plus delta minus delta plus delta naught equal to 0. That is the fourth equation. So this is non-dimensional third equation, non-dimensional fourth equation. I am just going to solve from these two equations. First, from equation 3, I am getting the value of theta. Theta is expressed as, if you look at here, theta we are expressing in terms of q1 bar b into delta divided by 1 minus q1 bar, and substituting theta into equation 4, whatever we obtained here, I am substituting the value of theta here. So if you look at theta, can after substituting theta in equation 4 and solving, we can get the value of delta. Delta is equal to delta naught divided by 1 minus, if you look at here, it will become BC into Q1 bar Q2 bar divided by 1 minus Q1 bar plus Q2 bar. This will be the value of delta. If you look at here, I have just given a the solution procedure here. I have just substituted in equation 4 Q2 into the theta here, C into Q1 bar B delta by 1 minus bar plus delta minus delta plus delta not equal to 0. So it will become Q1 bar Q2 bar B into capital C 1 divided by 1 minus Q1 bar into delta plus Q2 bar into delta minus delta plus delta not equal to 0. Then delta I have solved from here and taken common from here. So it will be delta is equal to delta naught divided by 1 minus second bracket B capital B C Q1 bar Q1 Q2 divided by this will be also Q1 bar Q2 bar. So BC into Q1 bar Q2 bar divided by 1 minus Q1 bar plus Q2 bar. So this is our value of delta, and substituting the value of theta in the delta in the first equation, we can get the value of delta theta. So after simplification, we are getting delta is equal to 1 minus q1 bar into delta naught, and the denominator will be 1 minus q1 bar multiplied by 1 minus q2 bar minus bc q1 bar q2 bar. Just if you look at here, I have just simplified this expression. This expression, if you simplify, it will become 1 minus q1 bar into delta naught, then whole thing denominator will be 1 minus q1 bar minus bc q1 bar q2 bar minus q2 bar into 1 minus q1 bar. After taking this and this, we will have 1 minus q1 bar multiplied by 1 minus q2 bar. So we will minus bc into q1 bar q2 bar, and substituting the value of delta. So similarly, we will be getting theta equal to q1 bar into capital B delta naught. This whole thing divided by 1 minus q1 bar into q2 bar minus bc q1 bar q2 bar. Is it okay? So there were two unknowns, theta and delta. We have we got two equilibrium equations. From these two equilibrium equations, just we have solved these two equations to find out the value of delta and theta. Is it okay up to this?
Okay, sir. Yes, sir. Yes, sir.
Okay. Okay. Then I am coming to the next part, the calculation of efficiency. So we'll be similarly we'll be calculating efficiency here. Aeroelastic efficiency means lift, aeroelastic lift LAE will be Q into C multiplied by CL alpha into theta and CL delta into delta, and similarly rigid part will be QC CL delta into delta naught. So after means taking the efficiency LAE by LR will be getting, after simplification will be getting, here it is equal to theta by CL delta bar plus delta, whole thing multiplied by 1 minus delta naught. Delta naught is coming from here. And now what we will be doing, we will be substituting the value of theta and delta. If you look at here, I have taken from these two equations theta and delta and substituted here. So it will be Q1 bar multiplied by B divided by CL delta bar plus 1 minus Q1 bar, and whole thing divided by 1 minus Q1 bar multiplied by 1 minus Q2 bar minus BC into Q1 bar Q2 bar. So this is our expression. Then finally after simplification we will be getting this expression 1 minus Q1 bar multiplied by 1 minus B into CL delta bar, this whole thing divided by the denominator part. And now we will be getting that control reversal. Control reversal when lift efficiency is equal to 0, equating the numerator part equal to 0, that will be giving us the control reversal. That's what I have taken it here. So if you look at 1 minus Q1 bar multiplied by 1 minus B divided by CL delta bar equal to 0. If we look at after simplification, finally we are getting the same expression, Q reversal is equal to minus QD wing multiplied by CL delta bar divided by CM delta bar. Okay, I am stopping here. If you have any doubt, you can ask me, or next day you can ask me the questions if you have any doubt. I just take the attendance after this.